Thermal stress. The stress developed in a rod fixed at its two ends against the compressive strain due to the external forces provided by the rigid support at the ends is called thermal stress. If the temperature is increased by delta T, then fractional change in length would be delta L by L equals to alpha L into delta T, equation 1. Now, Young's modulus of elasticity Y equals to delta F by A, stress by strain equals to delta F by A divided by delta L by L equals to delta F into L by A into delta L, or delta F by A equals to Y into delta L by L equals to Y into alpha L into delta T, equation 2. Hence thermal stress delta F equals to A into Y into alpha L into delta T, equation 3. Here A is the area of cross section of given area of cross section of the metallic rod. Y is the Young modulus of elasticity of the rod, and alpha L is the coefficient of linear expansion. Delta T is the change in temperature. Question: a steel rod of length 5 meter and area of cross section 40 centimeter square is prevented from expanding while the temperature rises by 10 degrees Celsius. Find the thermal stress developed in the rod and external force acting on its fixed end. The coefficient of linear expansion of a steel is 1.2 into 10 to the power minus 5 per Kelvin, and Young's modulus of elasticity for a steel is 2 into 10 to the power 9 Newton per meter square. Solution: we have delta F by A equals to Y into alpha L into delta T. Putting these values, given values 2 into 10 to the power 11 into 2 into 10 to the power minus 5 into 10 equals to 2.4 into 10 to the power 7 Newton per meter square. Hence delta F A into Y into alpha L into delta T equals to 40 into 10 to the power minus 4 into 2.4 into 10 to the power 7 equals to 9.6 into 10 to the power 4 Newton, equivalent to 10 to the power 5 Newton. Thus, the stress developed in the rod is equal to the 10 to the power 5 Newton. Stress. External force. External force acting on the ends of the rod is equal to 10 to the power 5 Newton. Examples show that the coefficient of area of expansion delta A by A into delta T of a rectangular sheet of the solid is twice its linear expansivity alpha L. The figure 1 shows a sheet of length A and width B, and the same in the figure 2 the same sheet is shown when its length has increased by delta A and its width is increased by delta B. Now from figure 2, increase in area due to areal expansion, delta A equals to delta A1 plus delta A2 plus delta A3 equals to delta A1 equals to A into delta B plus B into delta A plus delta A into delta B equals to A into alpha L B into delta T and plus B into alpha L A into delta T plus alpha L A into delta T into alpha L B into delta T equals to 2AB into alpha L into delta T plus alpha L square AB into delta T का whole square equals to AB into under bracket 2 alpha L plus alpha L square delta T and bracket closed into delta T equals to A into 2 alpha under bracket 2 alpha L plus alpha L square into delta T bracket close into delta T. Now as alpha L is very small, so alpha L square into delta T will be very small in comparison to 2 alpha L and hence can be neglected. Thus delta A equals to A into 2 into alpha L into delta T, or delta A by A into 1 by delta T equals to 2 into alpha L equals to alpha A equals to coefficient of radial expansion. Proved. Now next example. A blacksmith fixes iron ring on the rim of the wooden wheel of a bullock cart. The diameter of the ring and the iron ring are 5.43 meter and 5.231 meter respectively at 27 degrees Celsius. To what temperature should the ring be heated so as to fit the rim of the wheel? The given alpha L for iron is 1.2 into 10 to the power minus 5 per Kelvin. Solution: we have L equals to, that is length of the ring, equals to 2 pi r. This implies L proportional to r. Diameter of the wooden ring 5.243 meter and diameter of the metal ring 5.231 meter. Thus d1 equals to 5.231 and d2 equals to 5.243. Now from the formula of linear expansion, d2 equals to d1 into under bracket 1 plus alpha L into t2 minus t1. Given t1 equals to 27 degrees Celsius, then t2 equals to what? Now from equation 1 we can write 1 plus alpha L into t2 minus t1 equals to d2 by d1. This implies alpha L into t2 minus t1 equals to d2 by d1 minus 1. This implies t2 minus t1 equals to under bracket d2 by d1 minus 1 into 1 by alpha L. Hence t2 equals to t1 plus under bracket d2 by d1 minus 1 into 1 by alpha L. Putting all values and solving, finally we get 27 plus 0.012 by 5.231 into 1 by 1.2 into 10 to the power 5 Kelvin answer. Our next topic is heat capacity. The amount of heat required to change the temperature of a given amount of substance through unity is called heat capacity of that substance. It is given as S equals to delta Q by delta T, where delta Q heat supplied to the substance to raise its temperature from T to T plus D delta T. Unit Joule per Kelvin, SI unit, and another unit is calorie per degree Celsius. Now dimensional formula is ml to T minus 2 per Kelvin. Elementary form S equals to dq by dt. Next is a specific heat or a specific heat capacity. The amount of heat required to change the temperature of unit mass of a substance through unit degree is called a specific heat capacity of that substance. It is given as small s equals to cap S by m equals to 1 by m delta Q by delta T. In elementary form, S equals to dq by m dt, where cap S is the heat capacity, small m is the mass of substance, delta Q is the heat supplied to the substance or rejected, and delta T equal to change in temperature. SI unit is joule per kg per Kelvin, and another unit is calorie per gram per degree Celsius, and its dimensional formula is m0L2T minus 2K minus 1. Molar specific heat capacity. It is defined as the heat capacity per mole of the substance and given as C equals to S by mu equals to 1 by mu delta Q by delta T. In elementary form, C equals to 1 by mu into dq by dt, where C equals to molar specific heat capacity, mu equals to number of moles, delta Q equals to heat supplied to or rejected from substance, delta T equals to change in temperature, SI unit joule per mole per Kelvin, and dimensional formula m0L2T minus 2K minus 1. Next, molar specific heat capacity at constant pressure Cp. The amount of heat required to change the temperature of unit mole of substance, may be gas, through unit degree, keeping the pressure constant, is called a specific heat capacity at constant pressure. Thus Cp equals to 1 by mu dq by dt. And molar specific heat capacity at constant volume Cv. The amount of heat required to change the temperature of unit mole of substance gas through unit degree, keeping the volume of substance constant, is called a specific heat capacity at constant volume. Cv equals to 1 by mu dq by dt. Question: why water is used as the coolant in automobile radiator as well as a heater in the hot water bags? Answer: it has highest specific heat capacity value, that is 4186 joule per kg per Kelvin. So it absorbs maximum heat to raise its own temperature by unity. So it absorbs maximum heat to raise its own temperature by unity. So water is used as the coolant in automobile radiator as well as a heater in hot water bags. Definition of calorie. The amount of heat required to raise the temperature of 1 gram of pure water through 1 degree Celsius from 40.5 degrees Celsius to 15.5 degrees Celsius is called 1 calorie. Now change of a state. Matter normally exists in 3 states: solid, liquid and gas. A transition from one of these states to another state is called a change of state. Example: solid to liquid and liquid to vapor, a vapor state, and vice versa. During the change of a state, transfer of heat takes place and temperature of the system remains constant. For example, let's event is solid to liquid, that is a solid body is changing to the liquid body, and this is called melting. And here melting point is 0 degrees Celsius for water. Again, liquid to solid, fusion, and for its melting point is 0 degrees Celsius. Similarly, liquid to vapor is called vaporization, and also boiling point 100 Celsius for water. And vapor to liquid is called condensation, and its boiling point is condensation or boiling point, or both are same. For water is 100 degrees Celsius. Both of the substances coexist in thermal equilibrium during the change of states. Normal melting point. The melting point of a substance at a standard atmospheric pressure is called its normal melting point. Question: why skating is possible on snow? Answer: skating is possible on snow due to the formation of water below the skates. Water is formed due to increase of pressure and it acts as a lubricant. Sublimation. The change from solid state to vapor state. The change from solid state to vapor state without passing through the liquid state is called sublimation, and the substance is called sublimed. Example: dry ice, solid CO2, iodine, etc. Latent heat. The amount of heat per unit mass transferred during change of state of substance is called latent heat of the substance for the process. For example, latent heat of fusion or melting, LF. It is the heat transferred per unit mass during the change of a state from liquid to solid or from solid to liquid. It is given by LF equals to delta Q by M, where delta Q heat transferred during change of a state and M is the mass of the substance. Unit is calorie per gram or joule per kg in SI. Now for water ice, LF equals to latent heat of fusion or melting, 80 calorie per gram in CGS or 80 kilocalorie per kg, and in joule and in SI unit LF is 3.33 into 10 to the power 5 joule per kg for water ice. Latent heat of vaporization or condensation, LV. Latent heat of vaporization or condensation, LV. It is the heat transferred per unit mass during the change of a state from liquid to vapor or vapor to liquid. It is given as LV equals to delta Q by M. For water vapor, LV equals to 536 calorie per gram or 22.6 into 10 to the power 5 joule per kg. Water equivalent of substance, mass of substance गुने specific heat of capacity of substance. A specific heat capacity of water, that is M water equals to Ms into Ss by Sw. Calorimetry.